So let's go back to when we had our magnetic field of a loop, and remember that this was specifically on the axis of the loop, so not for any point in space. And I had this fairly complicated form, but we can start to try to simplify this a little bit. So what we can do is consider really far distances, and that means that the distance we are from the center, remember that we have our loop, we're on the axis, and that basically this distance is z, where that distance is r. And if we're really far away, that's saying that z is much, much greater than r. We can simplify this term to basically say that the r doesn't matter, the r squared doesn't matter. And we can do this in a more mathematically rigorous way that I'm not worrying about at the moment. Z squared to the 3/2 power simply becomes z cubed. So we can basically cross this off and just replace that with z cubed to simplify a little bit. And that's going to give us our magnetic field on the axis as long as we're really far away, again from one of these current loops. Now, we can do a little bit of a trick of the math and notice that 2 became 4 pi and r squared became area. Now in this case, this is the area of a circle, which is pi r squared. We also gained this factor of 2 on top. So basically we multiplied both the bottom and the top by 2 pi. And so that's how we went from 2 to 4 pi, and we went on top from just r squared to 2a. So why would we do this? Why would we rearrange this? Well, now we have a new form. And one of the interesting things about this new form is how much it looks like the electric field from a dipole. And remember that a loop is simply a dipole. So now that we have this, we have to look a little bit and compare. Here we have mu naught over 4 pi, where before we had 1 over 4 pi epsilon naught. That's just how these constants work, and that's not that important. We have z cubed on bottom, we have z cubed on bottom. On top we have a factor of 2, and for the electric dipole, we had this term that was our dipole moment. You can see that our dipole moment here can probably be AI, the area times the current in our loop. The symbol we use for magnetic dipole moment is mu. And be careful because this should be mu vector, and that is different from mu naught, which is that permeability constant. So again, we don't have a lot of Greek letters, but somehow we're using the same ones over and over. Sorry. So be careful. Notice there are 2 different mu's here. They mean very different things. So it points from south to north. And so that actually gives us our direction. So in this case, the magnetic field direction matches the dipole direction as long as we're talking from south to north. And remember that north pole is where the field exits, and south pole is where it enters. So what that would look like in this little loop is you have your field entering, so this is your south, and then you have your field leaving, so this is your north. And you can actually check that really quick with the direction that the current is labeled to make sure that everything is in agreement. So it points from south to north, and the reason we actually care about this, rather than redefining the equation in this new way, is that magnetic dipole moment is going to appear in other calculations. So for instance, looking at force and looking at torque. And it's something that can be defined or can be measured even if the area is too small to see. And in this case, I'm waving my hands a little bit at this, but we can talk about, for instance, the magnetic moment of electrons, where it's actually a quantum mechanical quantity called spin. But so in that case, there's not really a current going in a ring, but there's something analogous in a quantum mechanical sense. So magnetic moment or magnetic dipole moment is a really important quantity that even shows up at kind of a particle physics, fundamental physics level. And at that point, we really don't have current going in circles, but we have charge doing something that involves circles, kind of. So this is a nice quantity, and it's nice to define it since, for instance, instead of having a perfect circle, you could have a square. You could have a strange short sort of shape. So keep that in mind, that once we've defined it this way, mu can have a very different form, but we can still, say, measure the value of mu and then plug it into these equations.